Algebra 2 Honors students. This is the first video that I'm making for your class. We are in section 8.6. We're going to do part 1 in this video. We're going to be talking about graphing radical functions. Specifically, we're going to do square root functions and cube root functions. So here we go. Let's embark on some fun together. As we're going along in the video, I'm encouraging you to be filling out the notes that you got in the math packet. So this is already on your paper. We're going to be graphing the square root of x. I've already got some numbers here carefully chosen. I'll talk about my choices in just a minute. So we are going to be filling those in. Now, as you're writing this down, you might be wondering to yourself, Ms. Wingard, why did you pick -9 or -4 or whatever? That's a good question, because what happens if I have that negative number underneath a radical? That's where the imaginary numbers come out. And so technically we can't do that because we would get an imaginary answer and we can't graph that. We can't do this one and we can't do this one either. But we can do the square root of 0. It's going to be 0. Square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. And so the reason I chose those numbers is because those were perfect squares. 16, 25, 36, 49, those would all be really good choices. Could you choose 5? Sure, but the square root of 5, you probably don't really know what that is. You might know that it's in between 2 and 3 and it's closer to the 2. But if I were you, I would stick with those perfect squares because they're a lot easier to figure out. So let's plot what we've got and go ahead and make sure that you always label your axes. This is going to be particularly important when you're doing homework and you have to graph and draw the axes. You need to make sure you're labeling them. So we have 0, 0, 1, 1, 4, 2, and 9, 3. So when I go to connect these, this looks completely different than any other graph we've had this year. It's not linear, it's not making a line, it's not quadratic because it's not a parabola. Remember, we did polynomials and we were getting things that looked like W's, M's, S's, N's. We did rational functions and we got some kind of cool looking graphs, but this one is totally different. Now you'll notice that I'm going to start right here. I'm going to curve it over and I'm going to put an arrow this way, but I'm not going to put an arrow here. And you might be wondering, why am I not putting the arrow here? Well, remember we just said I can't plug in those negative numbers because the square root of those numbers doesn't exist in the real set of numbers. That's where the imaginary numbers come in. So this point right here, 0, 0, that's really my starting point for the graph. It doesn't get to go any farther than that. But over here, we could have plugged in a 16 and a 25 and a 36. So it could keep going to the right and up. So let's talk about domain and range because those are going to be important with these problems. And we can see the domain and the range both in the table of values that we have and in our graph. So let's start by looking at the table of values. Where did the numbers begin to work? They began when we plugged in a 0, and then a 1, and a 4, and a 9. So I'm going to say that x is greater than or equal to 0. I wasn't allowed to have any of those negative numbers under there, but it started working once I plugged in a 0 and higher. If we look at the range, we see the same things happening. It starts at 0 and our y values get larger. So we're going to say y is greater than or equal to 0. We can see both of these in the graph. If we look at the domain, our x values start at 0 and they get bigger. If we look at the range, our y values start at 0 and then they get bigger. Not quickly getting bigger, but they are getting bigger. So you can identify that domain and range whether you're looking at the graph or at the table of values. So this is standard form for our square root functions. A lot of these letters look familiar. We've dealt with the A, the H, and the K this year. So the H, K is your starting point. So just like we saw a minute ago in this last example, the 0, 0. This would have been like me having a +0 or a -0 under the radical. And outside of the radical, it's like I'm adding nothing to it. So I would have gotten an H value of 0, a K value of 0, and that's exactly where the starting point for my graph is. Now, just as a reminder, H is always the opposite of what you see, and K is always exactly what you see. And this goes back to Hiavox. Remember, we have dealt with this since chapter 2. Got horizontal, those are inside of the function, and they're opposite. Vertical changes are outside of the function, and they're the same. So that's where this comes from. Again, this is just review. It says make a table of values, and you want what's underneath the radical. Remember, that's called a radicand. You want your radicand to be a perfect square. 1, 4, 9, 16, 25, all of those numbers. Now, the higher you get, the bigger your graph is going to be. So I might not suggest using 25, 36, 49, but if you want to make a big graph, you can. So let's apply that to example 2. Let's first start by finding our H and our K. The H is the opposite of what we see. I see a +1, so I'm going to turn that into a -1. The K is exactly what we see, so I see a -3. That means my K is a -3. So when I create a table of values, what I already know is my starting point is at -1, comma, -3. I don't need to show my work in the middle because I've already identified the H and the K, and I already know that's my starting point. So now what I want to do is I want to figure out some other numbers that need to go there. So here's where we take the radicand, the x plus 1, and I'm going to set it equal to those perfect squares that we talked about. So I'm going to set it equal to 1, I'm going to set it equal to 4, and I'm going to set it equal to 9. And the reason I'm doing that is because I'm going to solve for x, and I'm going to find out what number does x need to be in order to make what's underneath the radical a perfect square. So in all of these, I'm going to subtract a 1, and I'm getting 3 x values, and I'm going to plug those in over here. So I have a 0, a 3, and what was the last one? An 8. And those are the numbers that we're going to plug in now into the middle, and we're going to show our work. So here we go. Square root of 0 plus 1 minus 3. Square root of 3 plus 1 minus 3. Square root of 8 plus 1 minus 3. All right, so going back up here, 0 plus 1 is 1. The square root of 1 is 1. And 1 minus 3 is -2. 3 plus 1 is 4. The square root of 4 is 2. 2 minus 3 is -1. 8 plus 1 is 9. The square root of 9 is 3. And 3 minus 3 is 0. So now I have 4 ordered pairs that I'm going to graph. Again, label your axes. So we have -1, -3. We have 0, -2. We have 3, -1. And then we have 8, 0. We pretty much see the same graph that we did a moment ago. See that same shape? But what's changed is that our graph has moved to the left 1 and down 3. And remember, that goes back to Hiavox, us being able to talk about those transformations. So we're just going to connect them. Again, it's a curve. No arrow here because that's your starting point. But we do need to include our domain and our range. And you can do this either by looking at the picture or by looking at the table of values. I often think the table of values really is the easiest, but I like looking at the picture as well. Here we see that our x values started at -1 and then they got bigger. And so that's exactly what I'm going to write. X is greater than or equal to -1. And then for our range values, they started at -3 and they continue to get bigger. So I'm going to write y is greater than or equal to -3. And that's it for that example. All right, example number 3. Let's start by identifying H and K. H is going to be -3 because it's the opposite of what I see. K is going to be -4 because it's exactly what I see. So what I already know is my starting point. So I have -3, comma, -4. Now I need to figure out what other numbers are going to be plugged in for x. So remember, we're going to take that radicand and we're going to set it equal to those perfect squares. So I'm going to set it equal to 1, to 4, and to 9. And then I'm going to subtract 3 in all of those. So for this one, I'm going to get a -2. And then plug in a -2, a 1, and a 6. And now the middle is where I'm going to show my work. So let's talk while we're writing this down. Y'all can listen. I'll talk. So here we have already talked about the H and the K. What do you guys think is going to be happening because of the -3 out front? I want you to think about Hyobos and what we have learned this year about it. Two things are going to happen. Something's going to happen because of the negative sign, and something is going to happen because of the 3. So I want you to think about that while we're filling out our table of values. But let's get started with the table of values. So -2 plus 3 is 1. The square root of 1 is 1. So I have -3 times 1 minus 4. That gets me -3 minus 4, which is -7. So now I have a second ordered pair. Here I've got 1 plus 3, which is 4, and the square root of 4 is 2. Then I'm going to multiply that 2 times the -3. That gives us -6, and -6 minus 4 is -10. And lastly, we have 6 plus 3, which is 9. The square root of 9 is 3. And when I multiply that 3 times -3, I get -9, and -9 minus 4 is -13. So I'm going to go ahead and label my X and my Y axes. Let's talk for a second. Maybe by now you've remembered what's going on with that -3. The negative sign out front is going to give us a vertical reflection over the x-axis, and the 3 is going to give us a vertical stretch by a factor of 3. So let's see if that actually happens with our graph. So we have -3 comma -4. We have -2 comma -7. We have 1 comma -10. And then we have 6 comma -13. So it's going to go off of our graph a little bit. No big deal. So right away I noticed that this graph is going to go down instead of going up. So there's our vertical reflection that we identified should happen because of the negative sign. I also noticed that my points are farther apart because they've been stretched. So the 3 did in fact do what it was supposed to do. It stretched it by a factor of 3. Again, we're going to include the arrow right there because we could keep plugging in larger values for x. So let's take it back to domain and range. So our domain started at -3 and our numbers got bigger. So x is greater than or equal to -3. Our range started at -4, but then our numbers didn't get bigger this time. They got even smaller. So we're going to say y is less than or equal to -4. And that's it. All right, so next example. Our H is 4. It's the opposite of what we see. Our K is 1. It's exactly what we see. So we already have a starting point of 4, comma 1. I want you to think in your mind what's going to happen because of the 2. So again, we're going to take our radicand. We're going to set it equal to those perfect squares so that we can find out what x is going to be allowed to be. I'm going to get a 5, an 8, and a 13. All right, let's plug them in. Okay, so 5 minus 4 is 1. The square root of 1 is 1. 2 times 1 is 2, and 2 plus 1 is 3. Next one, 8 minus 4 is 4. The square root of 4 is 2. 2 times 2 is 4, and 4 plus 1 is 5. And then last one, 13 minus 4 is 9. Square root of 9 is 3. 2 times 3 is 6, and 6 plus 1 is 7. So let's plot our points. We have 4, comma 1, 5, comma 3, 8, comma 5, 13. So on your paper, you might be able to do this a little bit better. I only have so much room, so I'm going to put it as far as I can go. 13, comma 7. So hopefully you recognize that the 2 was going to stretch it by a factor of 2. So it takes those points, spreads them further out. But again, we still have a starting point, and then we go forever in one direction. not to be confused with the band one direction. Let's talk domain and range. So if we look at our table of values, we're starting at 4, x's are getting bigger. So x is greater than or equal to 4. With our range, our smallest y value is 1 and the others get bigger, so y is greater than or equal to 1. All right, so we've talked about square root functions. Now let's talk about cube root functions. They're a little bit different. Obviously, we have now an index of 3. I've already pre-picked some numbers here. Let's plug them in and see what happens. Now with cube roots, because our index is odd, that changes the game a little bit. That does allow us to have negative numbers underneath the radical. Remember, you only get imaginary numbers if your index is even. That's when the i's come out. But if your index is odd, you can have a negative number. Because here's what this is asking us. This is just asking, what number will you multiply times itself 3 times to get negative 8? And that answer is negative 2. What number can you multiply 3 times to get negative 1? Negative 1. Then we would get a 0, a positive 1, and a positive 2. So for these problems, we can plug in anything we want. We can plug in negatives, we can plug in positives, we can even plug in zeros. There are no restrictions on our domain for cube root functions. So let's graph it and see what it's going to look like. We have negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, 8, 2. Here's what we get. We get, I kind of like to call it the horizontal snake. Now you may notice that I put arrows going in both directions, and there's a reason for that. Because I'm allowed to plug in negatives, because I'm allowed to plug in positives, it's going to go in both directions forever. So right away, domain, all real numbers. Because I have no restrictions. I can plug in whatever I want. Range, guess what's going to happen there? You may have guessed it, all real numbers. This graph, it's going to continue to go up, not very fast, but it's going up forever. And this is going down forever, also not very quickly. So it's going to hit all of our negative values in the range. It's going to hit all of our positive values in the range. And so we get both a domain and a range of all real numbers. So good to know, cube root functions, these are pretty easy. Domain and range are always all real numbers. Real quick, let me go back. You might be wondering, why did I pick those? Because those are perfect cubes. We could also have picked a negative 27, a positive 27, a negative 64, a positive 64, a negative 125, a positive 125. But I don't think you want to graph one quite that large. But you could if you really wanted to. All right, so standard form, it's the same thing that we saw with the square root functions, except now our index is 3. We have the h, we have the k, but this time we're not calling that the starting point because the h and the k is smack dab in the middle of your graph. So I'm calling it the middle point. So h, again, is still the opposite of what you see. K is still exactly what you see. Your value for A, that's either going to stretch it, compress it. Remember, I'm talking about Hiavas. It says make a table of values. This time you want your radicand to be equal to a perfect cube, not a perfect square. So positive 1, negative 1, positive 8, negative 8, those are typically the numbers that we want it to be equal to. So let's try it out with this problem. Our h is the opposite of what we see. Our k is exactly what we see. Now here's one thing that changes. When I go to make my table of values, this no longer represents the starting point, it represents the middle point. So guess where it's going to go in our table? It's going to go right in the middle. So 2, 1 is right in the middle. Now I'm going to take my radicand and I'm going to set it equal to those perfect cubes. So I'm going to set it equal to a negative 8, to a negative 1, to a positive 1, and a positive 8. And I'm going to find out what x can be. Well, x can be negative 6, it could be 1, it could be 3, and it could be 10. So negative 6 and 1. And then on the other side of 2, it could be a 3 or a 10. And so now we're going to show our work in the middle. So So let me get this written down, and you do so on your notes as well. All right, here we go with some math. So negative 6 minus 2 is negative 8. The cubed root of negative 8 is negative 2. And negative 2 plus 1 is negative 1. 1 minus 2 is negative 1. The cube root of negative 1 is negative 1. And negative 1 plus positive 1 is 0. 3 minus 2 is 1. The cube root of 1 is 1. And 1 plus 1 is 2. 10 minus 2 is 8. The cube root of 8 is 2. And 2 plus 1 gives us a 3. So let's go ahead and label x-axis, y-axis, and plot some points. We have negative 6, comma, negative 1, 1, comma, 0, 2, comma, 1, 3, comma, 2, and 10, comma, 3. And we see that same basic shape of what I like to refer to as the horizontal snake. Again, this gets arrows on each side, domain and range. You might remember they're both going to be what? You might be saying it right now. All real numbers. X and Y can be anything. All right, let's try another one. H is going to be negative 2. K is negative 1. Remember, this is no longer the starting point. It's the middle point. So we're going to put it in the middle of our table of values. So again, we're going to take that radicand and we're going to set it equal to those perfect cubes. So we're going to set it equal to negative 8, negative 1, 1, and 8. So we're going to get x values of a negative 10, a negative 3, a negative 1, and a 6. So negative 10, negative 3, negative 1, negative 6. And now let's show our work in the middle. So here we go. Okay, let's do some math. Negative 10 plus 2 is negative 8. The cube root of negative 8 is negative 2. 3 times negative 2 is negative 6. And negative 6 minus 1 is negative 7. Next one, negative 3 plus 2 is negative 1. Cube root of negative 1 is still negative 1. 3 times negative 1 is negative 3. And negative 3 minus 1 is negative 4. Negative 1 plus 2 is 1. Cube root of 1 is 1. 3 times 1 is 3, and 3 minus 1 is 2. Negative 6 plus 2, oh, I'm sorry, that's a positive 6. Whoops. And at that point, I would say, why didn't anybody correct me? And that's because you aren't in here with me. Okay, so now that I've got it corrected, 6 plus 2 is 8. The cube root of 8 is 2. 3 times 2 is 6, and 6 minus 1 is 5. Now let's plot these points. Again, don't forget to label your x-axis and your y-axis. So we have negative 10, negative 7. We have negative 3, negative 4. Negative 2, negative 1. Negative 1, comma 2. And 6, comma 5. So this thing got really stretched, right? It had a factor of 3 on the outside, so it really stretched those points. Again, domain, range, going to be all real numbers. How are we doing? Good, I hope. Okay, let's try another one. So H is 3, K is 2. That's going to be our middle point. All right, we're going to take that. We're going to set it equal. I'm not going to write it up there. Let's do it out loud. So x minus 3 equals negative 8. So if I add 3 to both sides, I get a negative 5. X minus 3 equals negative 1. So if I add 3 to both sides, I get a 2. X minus 3 is equal to positive 1. So if I add a 3 to both sides, I get 4. And lastly, x minus 3 is equal to 8. And if I add a 3 to both sides, I get 11. So let's plug it in. So if we do some math, I'm going to go a little bit faster on this one. We're going to end up with a negative 2 times a negative 2, which is 4, and 4 plus 2 is 6. Here we're going to end up with a negative 2 times a negative 1, which is 2, and 2 plus 2 is 4. Here we would end up with a negative 2 times 1, which is negative 2, and if I add 2 to that, I get a 0. And the last one, I'm going to end up with negative 2 times 2, and that turns into negative 4, and negative 4 plus 2 is negative 2. So let's see what's going on. So a couple of things that we know should be happening. We're going to have a horizontal shift 3 units to the right. That means instead of being at the origin, we're going to go to the right 3. We're going to have a vertical shift up 2 units. We're going to have a vertical stretch by a factor of 2, and that negative sign out front is going to mean that we're going to have a reflection over the x-axis. So let's see if that actually works out. So we have negative 5, comma 6, 2, comma, oh, wrong way, 2, comma 4, 3, comma 2, 4, comma 0, and then 11, so a little bit off my grid, 11, comma, negative 2. So I am seeing a stretch. I'm seeing that the middle is not here at the origin. It has been shifted 3 to the right and 2 up. And then I'm also seeing that reflection. So instead of it going from low to high, the reflection is making it go from high. Oh, I missed the points. That was bad. Let's try that again. There we go. Much nicer. And again, domain and range are all real numbers. Okay, let's get away from graphing for just a minute, shall we? And we have some problems where we're being asked to find the domain. So let's talk about what we know. Remember that we said that this thing right here that we call the radicand, we said that the radicand, when your index is even, and remember there's nothing there, that's understood to be a 2. So the radicand, when your index is even, means that you can't have a negative under there. Well, what can you have if it's not negative? That means you can have a positive. It also means that you can have 0. So your radicand, and this is just when your index is even, your radicand is going to be greater than or equal to 0. That's what that means. Has to be positive or equal to 0. So I'm going to take that 2x minus 5, and I'm going to set it greater than or equal to 0. Now the great thing here is this is just a linear inequality. Linear meaning it fits into the y equals mx plus b form. It would graph and produce a line. So we just have to solve it like we normally would. So I'm going to add 5 to each side, and then I'm going to divide by 2, and we would find out that our domain is that x has to be any number larger than or equal to 5 halves, 2.5, 2.5. That would be our domain. So when you have a linear function, pretty easy. Same thing here. We're going to take that. Again, our index is 2. That's even, so we're going to say that this has to be greater than or equal to 0. Well, if you want, you can do the distributive property. So we have 3x minus 6 is greater than or equal to 0. I'm going to move the 6 over using addition. And then I'm going to move the 3 over by dividing. And I would say that this domain is x is greater than or equal to 2. Those are pretty easy, right? Because they're linear functions. But let's get into what happens if they're not linear anymore. So if I take a look at this radicand, it is not linear because of this guy right here. Remember, that's what makes it a quadratic. Quadratics means that your highest exponent for the variable is a 2. So we're going to start it the same way. We're going to have 6x But if it's not linear, and we've learned this in the past, and we've done a little bit of practice with this in this chapter, you have to do the number line test. Remember the number line test, where we're going to find out where does it equal 0. We're going to create a number line. We're going to pick some numbers and plug them in. That's what we're going to do. So let's get started, because the first thing we have to do is factor this. All right, so if we were going to factor this, we might jump into a sum and product chart. Our sum is negative 13, and our product is positive 30. So I need to figure out what two numbers can I add to get negative 13, and can I multiply to get positive 30, and those numbers are negative 10 and negative 3. Then I'm going to place them both over my leading coefficient of 6, and then I'm going to ask myself, can I reduce? Yes, I can, because this turns into negative 5/3, and this one turns into negative 1/2. And so now that means that my factors are 3x minus 5, and my other factor is 2x minus 1. So nice review of factoring right there. Now let's get to the number line test. Remember, you're going to take each of those, and you're going to set it equal to 0. And I'm going to do a little bit of math in my head here. If I added 5 and then divided by 3, I would get a 5/3. And if I added 1 and I divided by 2, I would get a 1/2. So I'm going to draw a number line. 1/2 is smaller, so it's going to be on the left. 5/3 is larger, it's going to be on the right. Here's where I have to pick numbers in each section. So what's something that's smaller than 1/2? 0. What's something in between 1/2 and 5/3? Well, 5/3 is 1 2/3, so that means that the whole number 1 is in between there. And then over here I could plug in a 2, because this isn't quite 2. I'm going to take those numbers. I'm going to go up here. I like to go to factored form, so I'm going to go to factored form and plug it in. So bear along with me here. I'm going to plug in a 0. So 3 times 0 is 0. 0 minus 5 is negative 5. 2 times 0 is 0, and 0 minus 1 is negative 1. So I end up with a negative number times a negative number, which gives me a positive number. Remember, when we've done these, we said we don't really care what the number is. We just care about what the sign is. We want to know if it's positive or if it's negative. That's the goal. So it doesn't really matter that it was a positive 5. I just need to know that it's positive. Now let's plug in a 1. So going back here, 3 times 1 is 3. 3 minus 5 is negative 2. 2 times 1 is 2. 2 minus 1 is 1. And a negative times a positive is a negative. Again, I don't care what the number is. I just need the sign. Last one, we're going to plug in a 2. 3 times 2 is 6. 6 minus 5 is 1. 2 times 2 is 4, and 4 minus 1 is 3, and 1 times 3 is certainly a positive answer. Now, why are we going through all of this? Well, let me remind you that we said that our radicand has to be greater than or equal to 0. That means it has to be positive. So I'm looking for where on my graph do I get positive answers. I get it over here on the left. I also get it over here on the right, and because I have the or equal to bar, that means I get to include the 1/2, and I get to include the 5/3. So now that I have my number line tests accurately done, now I just have to write my solution. Well, how do I write this? I'm going to say that x is less than or equal to 1/2, because that's where I shaded, to the left of 1/2, or x is greater than or equal to 5/3. Again, because I shaded to the right of 5/3. So there's my solution for that. So this is a really good refresher, because we just kind of worked on some of these types of problems right before our communication. All right, so let's jump into this last one. Should be a little bit quicker. Again, we're going to take this guy, and we're going to say that it has to be greater than or equal to 0. Sum and product chart, some of you guys are really good at these fast. This would be x plus 3 and x plus 2. And so if you had a number line, if you were to set each of those factors equal to 0, you would get a negative 3 and a negative 2. Negative 3 is smaller, so it's on the left. Negative 2 is going to be on the right. I'm going to pick, let's say, a negative 4. Right here, I'm going to have to pick a fraction, so negative 2.5 or negative 2.5 or however you want to write it. And then over here, I'm going to pick a 0. You can pick a negative 1, but I love to use a 0 if I can use a 0. So now let's plug it in. Again, I like to go back to factored form, just to me it's faster. So negative 4 plus 3 is negative 1. Negative 4 plus 2 is negative 2. And a negative divided by, or sorry, a negative times a negative is a positive. All right, right here in the middle. Negative 2.5 plus 3 is going to be a positive 0.5. Negative 2.5 plus 2 is going to be a negative 0.5. Y'all, it doesn't matter what that number is. If you're not good with decimals, no big deal. You just need to know, is it positive or negative? And it's going to be negative. Last one, 0 plus 3 is 3. 0 plus 2 is 2. Positive times a positive gives me a positive. So I'm going back to that, and I'm saying, hey, what did I want? I wanted positives. So I'm going to be over here on the left, over here on the right, and I get to include the negative 3 and the negative 2 because I have the or equal to bar. So how do I write the answer? X is less than or equal to negative 3, or X is greater than or equal to negative 2. Okay, so I really don't remember what I assigned you for homework. I have all these classes going on in my head right now and I can't remember. So it's either a worksheet or book work. Whatever it is, do it. If you have questions, I would really like you to go to the website, go to the blog, type it in. I'm going to be getting to them as I can and as quickly as I can. Ask me your questions there. If it's in the book, I feel pretty certain that I assigned odd problems so that you can check your work. That's really important. I'm not concerned with you just getting the right answer. I want to make sure you understand why you're getting the right answer. And as you're doing this homework, if you'll take a picture of it when you're done and then send it to me through email, that would be great, and then I can give feedback. But let me know how you're doing. I'm not sure. I'm trying to remember what section comes next. I think it's part 2 of this, so I'll be making another video later, hopefully in different clothes because I'm a little warm in here. I see that I forgot to turn the air conditioner on, which makes total sense why I'm hot right now, and I've been in here making videos for a couple hours. So hopefully I'll look fresher next time you guys see me. So I'll see you on the next video. Bye.